In this lecture, we're going to cover object-oriented programming. We'll focus a little bit on how it applies to Python, but primarily we'll be focused on the concepts here. We'll leave the application to, for Python to LinkedIn Learning modules and other online resources. We'll discuss what is object-oriented programming, the paradigm itself, why it's important, and how it's useful in business. We'll talk about the differences between classes and objects. We'll look at the differences, or rather the aspects of objects and classes called properties and methods. And we'll also compare object-oriented programming to structured programming and the benefits that it brings. Object theory, or the object-oriented paradigm, is exactly that. It's a paradigm. So let's break this down pretty quickly. A paradigm can be a buzzword. It's also a set of assumptions, concepts, and values that really just give us a worldview. They give us a pattern of thinking and a common set of principles and ideas that can be shared and built upon. Object-oriented design and development is a technique used to both conceptualize and construct an application as a collection of objects that interact by passing messages. What this means is that the object-oriented design provides a set of principles and patterns based on objects that are used to maintain their state, encapsulate their functionality, and more easily represent the physical world. This will become much more clear as we explore what the principles are and how they're used in real solutions. With a bit of practice and some review of the terms, it will become much more obvious as to the advantages and intentions of designing and developing using this technique. And not just for code. You'll be surprised to learn that you've been leveraging some object-oriented patterns and components already without even knowing it. If you've done any programming in Python, JavaScript, or C#, any of the .NET languages, those are object-oriented. And some of the entity design you've done with SQL Server and other relational databases may have also used object-oriented principles. One of the first principles we need to understand in terms of object-oriented design are classes and objects. Classes represent the blueprint, as they specify what the type of object looks like in terms of its features, its behaviors, and its attributes. An object, on the other hand, is a particular instantiation of a class. So, just like we can have a blueprint of a house, which is the representation of all the features of the house, it is not itself a house. We have one blueprint, and yet we can create many houses from that same blueprint. Each house in this example is an object, while the blueprint is the class. We'll look at a few more examples. Let's take a look at a more concrete example of a class versus an object. In the case here, the item on the left is a car class. It defines three attributes: manufacturer, horsepower, and color. And it also has two functions: honk horn and rev engine. The class just tells us what we can expect when we create a car object or if we are given a car object. The item on the right is an instance of the car class. It's a car object. Notice that it has an attribute called manufacturer as defined by the class, but in this case, that property, that attribute, has a value, Toyota. Likewise, we can look at the other attributes of the car, horsepower and color, and see that these also have values. What's more, rather than just telling us that we can ask the car to honk the horn, the noise it makes when the horn is honked is also implemented in the car object. Same with the rev engine. So let's back up a minute. What do I mean when I say we create or we're given a car object? Well, just like when we create a variable to hold an integer or a string, we can create a variable which holds a car object. Unlike strings and integers, though, our car is a bit more complex. The car object needs to know what type of car it is. That's the manufacturer. how many horsepower it has, the color of the car in order to be useful. And because an object is really just stored in a variable, our car can be passed around through the program in the typical ways, like as a parameter to a function, as a local variable, or even as part of a list or a dictionary. An object can also be stored in a file. We'll talk about that a little later when we talk about how this gets implemented in Python. And what's more, an object can be assigned as an attribute of another object. We could, for instance, create an attribute of the car that contained all of the details of a manufacturer. But now we're getting a little ahead of ourselves. I need to be clear for a second. Through the rest of this lecture, I'm going to describe the parts of an object. Since the structure of an object is the same as the defining class, you should keep this thought in mind. For instance, if I said my house is going to have a roof, you would know that both the blueprint for the house and the actual house have a roof. The blueprint, of course, just having a representation of the roof, and the actual house has a roof. I'll be explicit about talking about the differences when it becomes necessary. So we've talked about objects or classes having attributes. The attributes of an object are called properties, and they represent the exposed attributes or state of an object. The properties are defined in the class and then retrieved or set on the actual object. For instance, in our car example, we can think of lots of attributes of an automobile. A few that we talked about before and that are listed here include the manufacturer, the model, or the color. These things don't change very often, but also we have an attribute called current speed, which may change regularly. Using our automobile example, it's important to notice that the class, car, defines the placeholders and the types for the attributes, but the car object itself is what actually holds the value. In this case, we know our car is a red Toyota that has 200 horsepower. If we were to create another car, we would need to specify values for these three attributes as well. The other structural component of an object are the behaviors that allow us to interact with the object. Each class defines which methods are available to other objects in our program in the same way the class defines which attributes are exposed. In Python, methods are functions that are executed in the context of a given object. In other words, though we define the function start engine in the class, the engine is started on the specific car in which the method is called. We can also define the change gears function on the class car, but it is the object that we use, the specific instance of the object that we use in order to actually execute the change gears function. Once again, back to our class versus object discussion. On the left, we see the two methods, honk horn and rev engine. These methods are defined as placeholders on the class. And on the right, we see our object, the red Toyota, which beeps when the honk horn method is called and returns vroom when the rev engine sound is made. While we can default these values to all cars, for instance, the idea of being able to overwrite them and do something different in the actual object is what makes them valuable. Object-oriented programming is a little bit different than the structured programming that you've been used to seeing. In object-oriented programming, we focus on creating objects that have both data and behavior, and we promote modularity and reusability through classes and methods in structured coding. This centers around breaking down the problem into small, manageable tasks using functions and procedures, promoting a clear flow of control. Object-oriented programming is ideal for complex systems where real-world modeling and interaction are crucial, like game development simulations. Structured programming is well suited for small projects with straightforward tasks like writing scripts or simple utilities. Now, don't get me wrong. Oftentimes, complex programs are a combination of both these aspects, and even the simplest structured programming scripts can use objects. Most of these objects are ones that have been created already or have been structured into a whole new application. Among the many advantages of object-oriented programming, there are two key ingredients which make complex programs easier to manage: modularity and reusability. Modularity refers to code that is structured into independent components. They can be designed, tested, and implemented on their own and then brought together to form larger components. Reusability refers to classes that offer definitions which can be used in part of larger components or in different solutions. Once a component is known to work, it can be reused in other applications. Think of modularity like building with Lego bricks. Each Lego brick is a self-contained piece with its own shape and purpose. You can snap these bricks together to create all sorts of amazing structures, from houses to spaceships. Now, replace Lego bricks with blocks of code, and you've got the idea of modularity in programming. In programming, modularity means breaking down a big task into smaller, manageable blocks of code. Each block, just like a Lego brick, does its specific job. These blocks can be put together in different combinations to build complex programs. Just as you can swap out Lego bricks to change your creation, you can easily replace or update these code blocks without affecting the whole program. Modularity makes it easier for building. And just like you can build more quickly with Lego bricks, modularity makes coding faster. You can work on individual code blocks separately, making it easier to understand and troubleshoot. The reusability brought ahead by modularity. Have you ever noticed how you can use the same Lego brick in different structures? In programming, you can reuse code blocks in multiple parts of your program or even different projects. No need to reinvent the wheel every time. You can upgrade without chaos. Imagine you built a Lego castle and you want to add a tower. You don't need to rebuild the entire castle. Similarly, when you want to upgrade or add a feature to your program, you only modify or add the specific code blocks involved, not the entire code base. And also, it makes maintenance much easier. Lego creations can sometimes break, right? Fixing or changing a broken part doesn't mean rebuilding everything. In programming, if something goes wrong or needs improvement, you can focus on affected code block, leaving the rest untouched. And the last way that modularity helps us is similar to working with friends on a Lego project. Programmers can work together seamlessly. Each person can focus on their code blocks, and when they're combined, they create something fantastic. Modularity is like having a big box of versatile Lego bricks for coding. It helps you build and maintain programs more efficiently, encourages reuse, and makes teamwork a breeze. With modularity, you can construct impressive digital structures without worrying about everything falling apart if you need to make changes. Two more concepts make that modularity and reusability come to life. These are called encapsulation and abstraction. If you imagine your code as a medieval castle, encapsulation is the fortified wall protecting the valuable data within inside. Just as knights guard the castle, classes guard data by controlling access through the methods. In object-oriented programming, encapsulation prevents unauthorized meddling and ensures controlled interactions. With abstraction, you show only the magic. Think of your smartphone. You don't need to understand every chip to use the apps on your phone. Abstraction provides a clean, simplified interface, hiding intricate implementation details. In object-oriented programming, abstraction emphasizes what an object does, concealing the complexities of how it is done. Together, they form a powerful duo. Encapsulation maintains the integrity of the data, preventing accidental corruption and promoting a clean structure, while abstraction enables modular design, letting you change what's inside without affecting how the outside works. The important takeaway here: encapsulation is like a fortress. It protects data with controlled access, and abstraction presents a user-friendly facade hiding the complex internals. You may be asking yourself, why are we spending so much time on object-oriented programming in a class on data management? Most programs today with any complexity are using some aspects or principles of object-oriented programming, and much of what we will be working with is going to present itself as objects in our solution. These same concepts make it super easy to translate our design to a data model as well as an object model. It's really easy to go from a user story to an object-oriented world when someone describes to us, for instance, how a user will interact with the screen. We can think of the user as an object, the screen as an object, and maybe the thing that's being edited on the screen is an object that matches something in real life. For instance, a product, an item in a catalog, and the catalog itself is an object. What are the properties of those objects in the catalog and the items as well? Those are the properties that we want to keep track of for items and catalogs in real life. It becomes very easy to kind of map our real world to a systems design. If we think in terms of objects, we can model the database to match. So it doesn't matter if we're using a relational database, we're using an object-oriented database, a graph database, or something unstructured like MongoDB. Third, it becomes trivial to save and import our data in a format that's consistent and readable, which is really important. XML, JSON, YAML, and many other file formats are both readable by humans with a simple text editor and provide the structure that makes it super simple to program or super simple to model rather in a computer program. In this lesson, we've looked at what is object-oriented programming. We've discussed the difference between classes and objects, classes being the blueprint and objects being the implementation of the blueprint. We talked about the structural building blocks which help define classes in Python, properties, and methods. We looked at how object-oriented programming is different than structural approaches and understood that sometimes structured programs use object-oriented techniques, or at least objects in their algorithms, and object-oriented programming really encapsulates some structural approaches in the objects. And we've considered two advantages of object-oriented programming, namely modularity and reusability, and two concepts as well, which help modularity and reusability work, called encapsulation and abstraction. Finally, we closed out seeing how object-oriented programming and the object-oriented paradigm can reflect itself not just in our code, but also in our data design and how we save and retrieve files. In the next lesson, we're going to focus on a few concepts that are important to object-oriented programming, and specifically about how we think about objects. We'll look at a concept called inheritance, a technique that allows us to specialize more general classes to hone in on details. Additionally, we'll take a look at polymorphism. There's a $2 word for you. Where we can specialize not just the properties, but also the implementations of the methods. And we'll take a look at some code in Python and understand how to read the code. We're not ready to create our own just yet. We just want to be able to look at some code and be able to predict how we expect it to work.